Hello and welcome to this revision session for paper 3 in A-level physics. So in today's revision session what we're going to be looking at is how to answer examination style questions for AQA physics paper 3. So if we've been successful and we've learned in today's lesson, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics and understand what topics we need to improve upon for A-level physics. So how should you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the question in the revision session. When you're doing this, make sure to write your answers out in full sentences and show your full working out. Whilst in the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from the revision session. And after the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising AQA A-level physics? The first thing you need to be doing is learning the key facts, understanding the knowledge of the course. So use revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Secondly, you should be retrieving your understanding by testing yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge. And then finally, the third step is practicing by having a go at exam style questions. So use exam prep books, homework books, supervised study books and additional workbooks to answer exam questions and to mark your own work. So these three steps of learning the key facts, testing yourself and practicing exam style questions are how you should be revising A-level physics. So let's have a look at some revision questions for the practical aspect of physics paper 3. So the first question says the apparatus in figure 7 is used to determine the mass m of a load using the principle of moments. A uniform metal tube of weight W is kept horizontal by a supporter P and by a vertical force F applied by a force meter Q. Now P and Q are at the same distance from their respective ends of the metal tube. A load of mass M is suspended from the metal tube at a distance A from P. The distance between P and Q is B. So the distance A is varied over the range of 0.100 meters to 0.700 meters. The force F needed to keep the metal tube horizontal is measured for each value of A. Throughout the experiment, B equals 0.800 meters. So show by taking moments about P that F equals mg over B times by A plus W over 2. So pause the video now, then when you want to go through the answer, unpause the video. Right, so how do you answer this particular question? Well, it's understanding what the principle of moments is, and it's the idea that because it's being kept horizontally, we must know that the moments clockwise will equal the moments anti-clockwise. So what we can say is how to work out a moment is going to be the force times by the distance from your particular point you're taking your moments about, which in this case is P. So we know that the anti-clockwise moment is going to be F times by the distance of B, because that is the distance, if you see previously, between F and P, and that is causing an anti-clockwise moment. Now in the next point, what's causing our clockwise moments? Well, it's going to be M. Okay, but that's not the force, that's just the mass. So the force is going to be mg, it's going to be the weight. So it's going to be mg times by a distance of A, and it's also going to be W times by B over 2, because what in fact is W? It's the weight, and you should always remember that for a uniform object there's going to be a weight acting at the center of mass, which we can consider to be the center of the object. So that's going to be B over 2 away from P. So you add those two ideas and you equate them to the anti-clockwise moment. You can then rearrange to make F the subject and you get your answer out. The next question now says that figure 8 is a plot of F against A. So draw a best fit line on figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, as we'll see throughout this particular revision session, it's a very common question to ask you to draw a line of best fit on graphs. So here you should be looking at a good line of best fit. So it should be accurately following the trend with an even scatter of points on either side. So you'd be looking at an intercept of tracing it back through of about between 1 and 1.2 newtons. Now the next question says, from this idea, determine M. So you might need to look back onto the previous screen to see that, and then the force meter has a 0 error. Determine using figure 8, so from the previous screen, a value for the 0 error when W equals 2.6 newtons, and then explain whether the 0 error in the force meter has an effect on the value of M calculated in the previous question. So pause the video now, and you may need to go back to the previous screen to look at the graph, and then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you should see that if you look back at the graph here, we've got F over A, so we should know that the gradient of F over A, okay, is going to be in this instance, okay, as you'll know that in this idea that A is in fact the distance, okay, between the mass and point P. So as a result, you've got a distance and you've got a force there. So at that point, what you can do is, if you work out your gradient of your line as seen here. Now remember, when you're working out a gradient, you need to draw your gradient triangle on the graph and make it as large as possible. Then you should work out your gradient. So at that point, we know that our gradient is going to be a force over that particular distance. So what we can then do is we can then use this to work out the calculation of M in mass, and then you can work it through to be about 0.65 or 0.68, because what you can do is, if you look back, you can work through, okay, what the value is going to be from the previous equation to work out your value of M. So you get between like 0.65 and 0.68 kilograms. Again, it's very common in paper 3 style questions for you to have to work out values from equations given to you. Again, determine in the next question a value for the 0 error. So again, you can see quite clearly that the 0 error manifests itself, okay, as it doesn't go through the origin, it'll go through part of the y-axis. So you've got to find your idea of your of the graph to find the 0 error. So you get about 1 to 1.2 newtons. It's the y-intercept, and then what you can do is then use that to then work out what the value and the weight is going to be. So you get an error in about 0.2 to 0.6 newtons. Now, will this affect the mass? Well, it won't affect the mass, because as you mentioned before, a 0 error will affect the y-intercept or the x-intercept for your graph. It will not affect the gradient, so therefore the gradient is unaffected, and the gradient is what we use to ultimately calculate M, so would not affect it. The next question says, technetium-99 is a radioactive isotope used in hospitals. Identify the type of radiation that is emitted when technetium-99 nuclei de-excites. Then, samples of technetium are prepared at a hospital from a source of a radioactive isotope, molybdenum, that is stored at the hospital. Figure 9 shows the generator that is used to prepare the sample of technetium. Water from a syringe passes through the molybdenum sample. The technetium-99 that forms from the decay of molybdenum, okay, dissolves in the water. The water containing technetium is collected in a lead storage container. Explain how the apparatus in figure 9 allows the safe handling of the collected sample. So pause the video now, then unpause the video when you want to go through your answer. Right, there will be certain questions which link into just knowledge and understanding from paper 1 and paper 2 on paper 3. So the first thing you've got to be aware is, as the technetium de-excites, because it's in a metastable state as indicated by the M next to the 99, it will be emitting gamma radiation. Now again, the paper 3 questions can sometimes ask about safety procedures needed for experimental procedures in physics. So how do you know it's got the safe handling? Well, the generator is shielded with lead. It makes a big deal of showing the fact that it's a lead storage container, so that's a very important idea. So this reduces the amount of radiation the user is exposed to, because some of the technetium will be releasing gamma radiation, and some of this gamma radiation will be blocked by the lead. The next question says, figure 10 shows a variation of the activity of molybdenum in the generator over an 80-hour period. A0 is the initial activity of the molybdenum in the generator. Estimate the half-life of molybdenum. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to work out values from graphs in Physics Paper 3 questions. So what you should be able to see is you've got a value for A0. So what you can then do is you can use this to work out a value for A0 over 2, which will then give you the half-life. So if you look to see how many squares it goes up to, so you can see that A0 goes up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So therefore A0 over 2, or half that, will go up to 5 squares. You can then read that across and you'll see that it's just over 64, so therefore it will be 66 hours. Now the next question says, figure 11 shows the activity of the molybdenum, and then a sample of technetium-99 is collected from the generator every 24 hours, causing the activity of the technetium in the generator to fall to 0. Sketch on figure 11 the activity of the technetium between the 24 hours and the 72 hours. So pause the video now, then unpause the video when you want to go through your answer. Like mentioned before, it'll be very important that you've got to be able to draw on graphs in Physics Paper 3. So what you'll notice is that it's being removed every 24 hours. So we're going to have 2 more of these particular cycles, and they'll follow the same particular curve that you see previously. So it'll have the same shape as the other 2. However, they're going to be smaller values, because you should be aware that it's taken out quite a bit of it each time, so there'll be less technetium to go through. So you should be seeing peaks at 48 and 72 hours, so you'll see that added on 24 each time, and then they'll decrease in height because there's less of the sample present. Now the next question says, explain why a sample of technetium-99 is collected every 24 hours and not more frequently. So pause the video now, then unpause the video when you want to go through your answer. Right, in these types of questions, again, it's got you to think about the real world implications of what you're doing in the physics practical. So the idea is that technetium should be extracted when it's near or at its maximum activity. As a result, because you get the greatest generation they're collected. So as you can see, that is reached after 24 hours, which is why you should be doing, because if you take it before then, you just won't get enough of it for it to be worthwhile. Now the next question says, figure 10 shows the data from an experiment in which a copper wire was stretched by applying a known tensile force. The total extension of the wire was recorded for each value of the applied force. So again, draw a line of best fit on figure 12, then determine using figure 12 a value for the Young modulus of copper. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, firstly, to draw your line of best fit, you're going to have another well-drawn line of best fit, and you'll notice from the points here that it's going to be a linear graph to start off with, and it's then going to curve smoothly. You should know that as well from your previous understanding of the stress-strain graphs for things such as copper, that you'll be aware that it should be doing that straight line section first and then start to curve. Now again, the line should accurately follow the trend of the points and have an even scatter of points about the line. Now to work out the Young modulus, again you should know that for the Young modulus, that Young modulus is stress over strain, so it is the gradient of the line, but it has to be the gradient of the linear section of the line, because when it starts to curve you'll no longer have the ability to calculate the Young modulus. So you've then got to attempt to measure the gradient with a large gradient triangle on the linear part of the graph. And remember, we draw that gradient triangle to show we've averaged it over a number of values. We then work it through. Now again, remember to think about stresses in times 10 to the 8 and strain is in times 10 to the minus 3. So we get our answer to be about 1 times 10 to the 11. The next question says, describe how the uncertainty in your value for the Young modulus could be estimated from the graph, and then the area under stress strain graph represents the mechanical work done per unit volume on the material as it is deformed. The original length of the wire used in the investigation is 1.50 meters and its cross-sectional area is 0.397 millimeters squared. Determine the work done on the wire as its original length is increased by 6 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important that you are aware of how you can calculate uncertainty in a number of different methodologies, with things such as repeats, with things such as readings and measurements, but also in graphs. Now, it's important to know that you can work out your uncertainty by establishing the difference between your maximum gradient and your minimum gradient, okay, or the difference between the worst gradient and the best line gradient as well, and you can double it as such like that, and that allows you to work out your uncertainty. Now for this next question, you're gonna have to calculate values. So firstly, what you should be doing is, you can notice that the area under the stress strain graph represents the mechanical work done per unit volume. So what you can do is you can then work out the area, and you'll get your work done per unit volume. So what you can do is you can estimate the values and work it through, and then you work out your value under the graph. Then you need to times it by the volume, because it's per unit volume. Now again, if you look in the question, we've got a cross-sectional area, and we've got a length, so we can then work out the volume. Now again, think of it like a cylinder. Now the trick again is, it's in millimeters squared, the cross-sectional area, so you're going to have to convert millimeters squared into meters squared, and remember, it's not times 10 to the minus 3 in the conversion factor, but it'll be times 10 to the minus 6, because it's millimeters squared, so the 10 to the minus 3 is then doubled. So you can work out your volume like so, and then multiply it by that value. Now again, you think, where is that area you're going to work to? As shown in the mark scheme here, it will go up to the idea that strain is 4 times 10 to the minus 3, because that's how you can work it out, in the sense of, you're told the extension is 6 millimeters, so you can work out your strain by doing extension over the original length and doing 6 millimeters over 1.50 meters. Obviously convert one of them to either millimeters or meters to get your value out of strain, which is 4 times 10 to the minus 3. So work out your area up to the strain of 4 times 10 to the minus 3. Now the next question says, many cars have headlamps that switch on automatically when light levels become too low. Figure 11 is a circuit diagram showing a light dependent resistor, an LDR, being used as a light detecting sensor. The output voltage V1 from the circuit is used to control the headlamps. The resistance of the variable resistor can be adjusted to change the light level at which the headlamps switch on. The system is set to switch the headlamps on when the power of the light incident on the LDR is less than or equal to 12 milliwatts. The wavelength of the photons incident on the LDR is 550 nanometers. Calculate the number of photons incident on the LDR in 1 second when the headlamps just switch on. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to think about what values that you're aware of. So you know that you have the wavelengths. The first thing you can calculate is saying the energy is equal to hc over lambda, an equation you learnt in particles. And at that point, that gives you your energy value. Now again, remember lambda needs to be in meters, so it's 550 times 10 to the minus 9 meters. We can then say that the power is going to be the number of photons, as you can work it through, times by the energy. Now we know the power is going to be equal to 12 milliwatts, so 12 times 10 to the minus 3. So we've got an energy, we've got a power, so therefore the number of photons is going to be the power over the energy, and we get our answer out to be 3.3 times 10 to the 16. Now, figure 12 shows how the resistance RL of the LDR varies with the power of the light incident on it. V1 must at least be 8 volts for the headlamps to switch on. Determine the resistance of the variable resistor for the headlamps to switch on when the power of the light is 12 milliwatts. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to be able to do in this question is work out what value is needed from the graph to be working through. So straight away we can see that the value of RL is going to be 30 kilo ohms, because if we look up here we can see that the power is 12 milliwatts. So if we go up to 12 milliwatts and across on the graph, we'll see that our value is going to be 30 kilo ohms. So at this point we know that the resistance of RL, okay, is going to be 30 kilo ohms. We can then use the potential divider equation. So at this point we know from our question, if you can see here, that that the value of V1 must be 8 volts for it to switch on. So at that point, if we know that V1 is going to be 8, well, therefore we know that in the variable resistor it's going to be 4, because obviously it's 12 at the start. One's taken 8, so the other must take 4. So at that point, we know that V is directly proportional to R, so therefore R's value is going to be divided by 2 as such to work out our final answer. Okay, and then you can work it through. So you're using your potential divider equation. Now the next question says, an engineer wants to adjust the circuit so that the headlamps switch on when the light levels are greater. State and explain what adjustment is necessary. So pause the video now, then unpause the video when you want to go through your answer. Again, this is a very common exam style question where you need to explain what's going to happen in experimental setups based on your understanding of physics. So you'll notice that how we want to adjust the circuit so the headlamps switch on when the light levels are greater. So if you have greater light levels, well then the resistance of the LDR will decrease. That's a fact you just know. So therefore you've got to reduce the resistance of the variable resistor. And why is that? Well, that's so that the ratios of the resistances return to their original value, so that V1 returns to its original value, so therefore it will switch on when you need to, because there's a potential divider circuit. The next question says, figure 13 shows the apparatus used in an experiment to measure the speed, V, of sound in wood. Two microphones A and B are separated by distance D and are firmly clamped face down to the wooden bench top. The microphones are covered with soundproofing foam and connected to an electrical timer. The end of the beam top is struck sharply with the hammer to produce a pulse of sound which travels through the wood. The timer starts when this pulse is detected by A. The timer stops when the same pulse is detected by B. The timer records the time t taken by the sound pulse as to travel from A to B. So explain why soundproof foam is used to cover the microphones. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's a very common paper 3 style question to ask you to think about what's going on in the investigation and why certain steps are taken. Well, we use soundproofing foam to stop the microphone from picking up noises in the background or other sounds which could lead to interfering with the values that were taken. The next question says the measurement of t is repeated several times and table 1 shows the recorded values of t. Calculate the mean value of t and estimate the absolute uncertainty in your mean value of t, and the distance d is 0.75 meters. Calculate v. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is testing you on how you work out different values. So to work out the mean, you add up all the values and then divide by the number of values that you have. So in this case, it's going to be 5, but also you've always got to consider, are there any anomalous results, and they will be removed from your calculation, which you work it out to be 191. Now, how do you estimate the absolute uncertainty? Well, in this case, the absolute uncertainty when you've got a set of repeats is range divided by 2. So range is the biggest value minus the smallest value, then divided by 2, and we get plus or minus 15. Now, how do you then work if you've got a distance? How do you work out a velocity? Well, again, quite simply, we've got a time to be 191 microseconds, so 191 times 10 to the minus 6. We've got a distance of 0.75, so we can use the equation velocity as distance over time to work this out and get an answer of 3.9 times 10 to the 3 meters per second. The next question says the absolute uncertainty is d is plus or minus 0.01 meters. Estimate the percentage uncertainty in v. Then an increase in the value of d reduces the percentage uncertainty in its measurement. This increase in d also increases the value of d. Suggest why increase in d may not lead to a more accurate measurement of v. So pause the video now, then unpause the video when you want to go through your answer. Again, this is a very common question in physics paper 3. You've got to be able to calculate percentage uncertainties from absolute uncertainties. So you've got to work out your percentage uncertainty in d by doing the absolute over the value, your percentage uncertainty in t by doing your absolute uncertainty, which you calculated previously, divided by the mean value times by 100. So you've got your two percentage uncertainties there, so you should get 1.3% and 7.9%. Now, because velocity is distance over time to then find out the percentage uncertainty of the velocity. It's the percentage uncertainty of the distance plus the percentage uncertainty of time, because they are divided by each other, so you get 9.2%. Now, the increasing d may not lead to a more accurate measurement of v, because if you think about it, when you increase the distance, you've got to think about what's happening to the samples itself. So the amplitude will get weaker, so it won't trigger the microphone B as much. So the microphone sensitivity needs to be high, so this would trigger any noise awarded with it. So whilst you do have to consider how percentage uncertainty will change with values, you've got to consider how this change would affect your measurements of those values themselves. The next question says, a fuse wire is designed to melt when the current in the wire reaches a certain value. The fuse current, IF, is the minimum current that will cause a length of fuse wire to melt. A student is provided with a length of fuse wire in normal electrical equipment. Figure 1 shows the circuit symbol for the length of fuse wire. Draw a suitable circuit diagram that the student can use to determine IF. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in a paper 3 style question, you will be asked to draw circuit diagrams. So you need to have a working series circuit that will have a battery or a power supply. You'll need to think of a way in which you can alter the values in the circuit by either using a variable resistor, a variable power supply, or a potentiometer. And then you need to have an ammeter there. Now you'll notice it says how can you determine the currents. You don't need the voltmeter in there because that will be there for the potential difference. So you just need the ammeter in series. Now the next question says, the student is provided with 5 samples of fuse wire. The 5 wires are all made from the same material but have different diameters. The theory suggests that IF is related to the diameter d by the equation IF equals kd to the power 1.5, where k is a constant. So describe how the student could use the circuit that they've drawn in the question to test the validity of this equation. And your answer should include the measurements to be taken and the apparatus needed, details of the procedure, and how to test the validity of the equation. So pause the video now, then unpause the video when you want to go through your answer. It's a very common paper 3 style question to ask to write a plan to do an experiment to test out an equation that you had just been given. So to answer this question, you should really take all 3 different bullet points separately to then answer the questions in the paragraphs. So what you should be doing is, let's think about firstly about our measuring devices. So we need our screw gauge micrometer to then measure the wire diameters, because you notice that you've got diameter d in the equation, so you'll need that. We then need to measure the diameter in more than one place and in more than one direction to get our accurate results, so always consider accuracy. You'd then start with the resistor on a maximum value, and then the variable power supply on the minimum, and then increase the current slowly and record the maximum value before the wire breaks. So that's for one of the values there, and then you would repeat readings and calculate mean values for each diameter and each current. And then what you would do is you then need to plot your graph. Now this is where it's very important, because you are trying to work out a value, and you know, for example, that so you want to verify a value and you've got a power in the equation. Well, you know that if you draw a log against log graph of the 2 variables, in this case the current and the diameter in this particular equation, that the gradient of the line produced should be the power of the found in the equation. That's a very important thing to understand when you're looking at log graphs, that the log graph gradient should be the value of the power. So it's a very easy way to verify things. So you plot log I against log d, and what you should get is you should then get a gradient, a straight line with a gradient of 1.5. Now the next question says, a student is investigating the cooling of oil. She puts 250 grams of hot oil into a metal container and records the temperature theta of the oil for 300 seconds as it cools. Explain one feature of the container that will ensure a maximum rate of heat transfer from the oil to the surroundings at any given temperature difference. Draw a line of best fit for the data plotted, and explain how figure 2 together with other data can be used to determine the total heat transfer from the oil during the first 300 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to understand what things are required to have a high energy transfer. So either have thin metal walls or have a high thermal conductivity, and you could link it into an equation as shown here to then say how that is possible. Like we've mentioned before, it's a very common paper 3 style question to draw a line that best fit in for plotted data. So again, draw a nice smooth curve with the passing through all the points or near all the points with an even scatter of the points about the line. And then finally, how can you determine the total energy transfer? Well, what you've got to do is think about what does the graph give you. Well, the graph will give you the idea of temperatures and the idea of time. Now we can see here that the temperature is changing, so therefore it's the kinetic energy store of the particles that is changing, which can be worked out with the equation Q equals mc triangle T. So what is going to be our temperature? Well, you can see it at 0 and you can work it through at 300. That then allows you to work out the change in the temperature, delta theta or delta T. You can then use the equation Q equals mc delta theta to then work out your answer of about 12,400 joules. Now the next question says, show that the rate of change of temperature of the oil at the temperature of 45 degrees is approximately 0.1 kelvins per second. Then at a temperature of 45 degrees Celsius, the rate of heat transfer from the oil is 54 joules per second. Calculate the specific heat capacity of the oil. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's a very common question to find values based on graphs given to you in paper 3. So you'll see that the rate of change of temperature is going to be temperature divided by time, which you should see is the gradient of the line in the graph because it's y over x. But you've got a curve. So to then work out the gradient of the curve, you would draw a tangent to the curve of 45 degrees, use a large gradient triangle and work out the value of the gradient to get about 0.09 to 0.11 kelvins per second. And remember, kelvins and degrees Celsius have the same interval, so when you're working out a change like in a gradient, it's an interchangeable unit. Now in the next one, we're trying to work out the specific heat capacity. Now we're told that the rate of heat transfer, which is the power, the work done per time, okay, is 54. So we can therefore say that power is equal to mc delta theta all over delta t. Now straight away, m and c are constants, so we can just put them to the side of the equation. So therefore P equals mc delta theta over delta t, which is the gradient of the line, which is what you've just worked out. So at that point you can then work out C by saying that C is equal to P over m times by the gradient of the line produced, and you get your answer to be about 2000 or 2300 joules per kilogram degrees Celsius. Now the next question says, figure 3 shows the apparatus that a student used to measure the wavelength of a horizontal beam of monochromatic light. The light is initially reflected downwards by a glass plate towards the lens in the mirror. The light travels through the lens and the lower surface of the lens reflects some of the light upwards. The rest of the light continues to the mirror and is reflected upwards at the mirror surface. Light from the lower surface of the lens and light from the mirror surface then superpose to form a circular interference pattern that is photographed. So figure 4 shows an actual size photograph of the interference pattern. The pattern is a series of bright and dark circles called rings. The diameter of the nth bright ring on this actual size photograph is dn. So for example, the diameter of the 4th brightest ring is d4. The student makes a magnified image of the interference pattern that is 10 times larger than the actual size. Figure 5 shows the magnified image, and the diameter of the 4th bright ring, counting from the center of the magnified image, is d4. So the student uses a millimeter scale to measure d4 from the image. The student measures d4 as 44 millimeters. Calculate the percentage uncertainty in d4, then calculate, using your answer to the previous question, the absolute uncertainty in d4 squared. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing to note is you should see that to work out your percentage uncertainty, it's the absolute uncertainty divided by the value times by 100. Now in this case, you'll notice that it's going to be a measurement and not a reading, because you're looking at the object twice to take the value, once at the start on the left hand side and once at the end on the right hand side. So when it is a measurement, it is going to be one of the interval given, so therefore it's 1 millimeter over 45 44 millimeters times by 100, so the answer is 2.3%. Now it's in the next question, it's saying it's d4 squared. Now you should be aware that when you have a power in a uncertainty, that work out the final value in the percentage uncertainty is the percentage uncertainty is the percentage uncertainty of the value times by the power. So in this case it's going to be 2.3 times by 2, which gives us about 4.6%. We can then convert this back into the absolute uncertainty by working out 4.6% of 44 millimeters, the actual value. So you work it out to be 0.88. Now the next question says determine using figure 5 an accurate value for D9, the actual diameter of the 9th bright ring, and then the wavelength lambda of the monochromatic light is given by lambda is D9 squared minus D4 squared over 20R, where R is 3.40 plus or minus 0.01 meters, which is the radius of the curved surface of the lens. So calculate lambda. So pause the video now, then unpause the video when you want to go through your answer. Right, what's very important is you've got to be able to take measurements from things given to you in exam questions in physics paper 3. So to work it through, you're going to take 2 measurements taken. So you look from one end to the other end, and I would do it multiple times. Then you can divide and find an average, and then you can work it through to be about 7.5 to 7.8 millimeters. At that point, you can sub in all the values to your equation. Again, it's a very common question to be asked to sub in values which are mostly given in a question to an unknown equation you've never seen before in physics paper 3. So you take your value for D9, which you've just worked through. Now again, you need to convert your millimeters into meters, so don't forget that. You need to get your value for D4, given previously in the questions 44 millimeters. Remember, we convert millimeters into meters. Again, we then divide it by 20 times by 3.40. Again, that's given in the question, to work out lambda to be 5.4 times 10 to the minus 7. Now, the next question then says calculate the percentage uncertainty in your value for lambda, assuming that the absolute uncertainty in D9 squared is the same as the absolute uncertainty in D4 squared that you calculated previously. Then explain one advantage of using figure 5 rather than figure 4 to determine the value of lambda. Now, pause the video, then unpause the video when you want to go through your answer. Right, so how do you work it through? So you'll see from the previous equation that we had D9 squared in there and we had D4 squared in there. So straight away, when you've worked out your percentage uncertainties for D9 and for D4, you'll double each one. Now again, because they are subtracted from each other, you then add the absolute uncertainties when that has taken place. So we'll just have to convert that afterwards, so you can then work it through like so. So you work out your absolute uncertainty for D4 squared and D9 squared. You then add the two values together at that point, and then what you can do is then you can work out your uncertainty in R. So again, you've got your absolute, you've got your value there, so then do the absolute over the value times by 100 to get your percentage uncertainty. And again, because you've got the top value and the bottom value and the dividing, you'd add your percentage uncertainties to get your answer of 4.7%. Now the advantage is that in using figure 5 is that the absolute uncertainty in measuring D is not changing because you're still using the same measuring device and it's the same values. However, the percentage uncertainty has decreased because you're measuring larger numbers. Whenever you're measuring larger numbers without changing your measuring device, the absolute uncertainty is going to stay constant, whilst the percentage uncertainty is going to go down because you're doing an absolute uncertainty divided by a bigger number. So therefore, it will decrease your percentage uncertainty. So that brings us to the end of this revision session. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you very much for watching this revision session on A-level physics paper 3 for AQA. So thank you very much and have a lovely day.